Welcome back to calculus. Today we are looking at areas of surfaces of revolution. So back in sections 1 and 2, we took curves and regions and rotated the regions around axes. Well, we're going to throw away the regions. We're just going to work with a curve. We're going to take a curve and rotate it around, and it's going to make a shell. It's going to make a shell whose cross sections are circles. And so what we're going to do is we're going to add up all those circles basically to find the total surface area for the generated region. If you want to see examples, find a calculus book, take a look at the pictures in there because they are so much better than anything I would draw. All right, so we have formulas for these. One is when we rotate around the x-axis, and one is for rotation around the y-axis. So the formula for the x-axis is the integral from a to b of 2 pi times the function value of x times the square root of 1 plus f prime of x squared dx. That's a lot of fun. Basically, here's what it is. 2 pi r is the equation for the circumference of a circle. F of x is the radius of these circles. So we have 2 pi r. There's my circles. And then this is the arc length. So we're basically taking these circles and going all the way down the arc, the length of the arc, and we have an integral to put it all together. We have the same thing here with y. You'll just notice I use g instead of f, and c and d just to have some different letters running around. So let's jump into our first example. Our first example is going to use this first one, where we have a function of x here. We have y is equal to the square root of x. We want to rotate around the x-axis, and x is stuck in between those lovely numbers, 3/4 and 15/4. So setting up the integral, this is what it starts to look like. We have the integral from 3/4 to 15/4 of 2 pi times the square root of x, and then here's that nasty arc length. Now you'll notice I haven't taken the derivative of that function yet, and I haven't plugged it in. I took that all the way over to the side there, and I'm going to clean up this whole square root first, and then we'll bring it back. Okay, so you can see here I brought the cleaned up version back. Let's take a look at it. So the derivative, since this is x to the half power, is 1 over 2 square roots of x. Okay. Feel free to check that and take a look at it, but I promise that's what it is. And so I need to simplify this square root of 1 plus 1 over 2 square roots of x squared. So I square this second fraction, which just gives me 1 over 4x. And then I combined the 1 and the 4x. Basically, I turned the 1 into a fraction, which is 4x over 4x. And so then I had 4x plus 1 over 4x. Splitting the square root then gave me the square root of 4x plus 1 on the top. And the square root of 4x is 2 times the square root of x. All right, that was fun and exciting. And what's nice now is when I take that and bring it back and put it in here for this arc length, some really good stuff happens. I now have 2 pi square root of x times this nasty fraction, but look what happens. The 2's cancel out, the square root of x are the really important part, they cancel out, and so I'm just left with the integral from 3/4 to 15/4 of pi times the square root of 4x plus 1. And that's not terribly scary. Again, I treat this as a power, a half power, and so I raised it by 1, give me 3 halves. I put its reciprocal out front. I do have a chain rule here with that 4, so I have to multiply by its reciprocal as well. All told, I get 1/6 pi times 4x plus 1 to the 3 halves power, evaluated from 3/4 to 15/4. And because I was running out of room on the board, I didn't go through the work of plugging in those numbers here on the board for you, but your answer should end up being 28 pi over 3. So feel free to check it and make sure that you understand how the heck I got there. There you go, that's one example. I'm going to do one more. Okay, so for our last example of today, I want to look at this curve, x equal to 1/3, y to the 3 halves minus y to the half. It's going to be rotated around the y-axis from 1 to 3, y between 1 and 3. So we have the integral from 1 to 3 of 2 pi times our original function times the arc length, yay, which we still have to sort out. You can see I did figure it out. It's y plus 1 over 2y to the half power. So I'll go back and let's take a look at how I got from that square root to here. So first I need the derivative of x. So if I take the derivative of x over there, we get 1/2 y to the half minus 1 over 2 y to the half. Long story short, if you give it a common denominator of y to the half, this turns just into a y. So you get y minus 1 over 2y to the half. And then I threw it into the square root and start cleaning that up. So the square root of 1 plus y minus 1 over 2y to the half squared. So if you square that out, the top turns into y squared minus 2y plus 1. The bottom is 4y. Again, I gave it a common denominator, so that makes this 4y over 4y. So 4y minus 2y gives me a plus 2y, which is great because that then factors. We have y squared plus 2y plus 1. It factors to be y plus 1 squared. Really slick little trick there to make that perfect square. So now when I take the square root, I just get y plus 1 on the top, square root of 4 is 2, and then the square root of y on the bottom, which is great. I brought it back. You'll notice I did change that square root of y I had to a y to the half power. And what's super nice is that now, because this is on the bottom, we're going to subtract that half power from both of these. So we get 2 pi times 1/3 just plain y, because 3 halves minus a half is 1, minus just 1. Those y's went away. And then I split this one up with a 2, 1/2 y plus a half dy. I then decided, hey, you know what? Let's clean that mess up a little bit. I got rid of these 2's. Because we can distribute the 2 through just one set of parentheses. And I chose that one where I had the 2's on the bottom. All right, so when you multiply all this out, you get 1/3 y squared minus 2/3 y minus 1. And then we integrate it, so we get, again, raise your power by 1, 1/3 times another third from flipping that exponent over. It gives us 1/9 y cubed minus, raise this to a square, multiply by a half, gives us minus 1/3 y, and minus just y. And it's evaluated from 1 to 3, and since I am basically out of room, and I want you guys to think about this, go figure out what that answer is. All right, thank you. Have a wonderful day.